In this video, we're going to explore the four cornerstones of machine learning: data, models, training, and evaluation. We will also delve into key learning paradigms: supervised versus unsupervised, and model-based versus instance-based learning. The first component of machine learning is data. You can think of data as the raw material from which patterns and insights are derived. And we use this data to teach and train machine learning systems. The other component of machine learning is models. One thing which is very important about models is that they are abstract algorithmic structures or mathematical representations that they provide guidelines on how to learn from data. And this is very important because just by having a model, we are not inherently knowing or learning anything until we get to the training stage. Models are just there to tell us how we can learn from data. And once we go to the training stage, that's when we expose the model to data. And this allows us to adjust the internal parameters of these models to learn relationships and extract insights. And something else that is very important is that if we have some data that we want to learn from, we can simply memorize the entire data and we don't have to really even learn anything that is generalizable. But this is in contradiction with the basic goal of machine learning to be able to generalize to new or unseen data. Therefore, a very important component of machine learning after the training stage is evaluation, which is a systematic method of assessing the model's performance on unseen data. So this means that the data that we use for training and evaluation, they should be two different sets of data points. And evaluation helps us to identify areas for potential improvement, meaning that do we have to collect more data points? Do we have to change the assumptions or mathematical representations that we have in our models? So these four components here, they're actually very much related, and we have to think about them as a group that they work together. Okay, so now let's talk about types of machine learning. Machine learning models can be can be categorized based on the level of supervision they receive during training. And the level of supervision here refers to the amount and type of labeled data. In the case of a spam filtering system, we mentioned that we have the raw emails or text data, and then someone has to label these emails as a spam or not a spam. So this is a type of supervision, which means that we have supervised learning. And you can think of these as input-output pairs. So in this case, inputs are these raw emails in the form of text, and outputs or labels are spam versus not spam. And the goal is now to make predictions or classifications for new incoming emails. Another example of this is handwritten image recognition. So we're going to see throughout this course the USPS or MNIST data set where we have handwritten image data sets, and our goal is to label each of these as one of the digits that represent. Another important category is what is known as unsupervised learning. So in this case, it means that we do not have any kind of supervision and we are learning from unlabeled data. So this means that we may have some raw emails in the form of text, but nobody has labeled these as a spam or not a spam. And our goal is to automatically be able to cluster these emails and be identify which group corresponds to the ones that are suspicious and which ones are completely fine. You can also think of these in terms of, for example, clustering customers based on their purchasing behavior or reducing the dimensionality of data if we have, let's say, many different features or predictors for a classification problem, and we want to be able to reduce this number. So these are all cases where we do not have direct supervision in our data set. Something else which is also important here is that a lot of generative models, for example, such as like, ChatGPT and other types of similar models where they create fake images and fake videos, also fall under unsupervised learning as they learn patterns in raw data without any explicit labels or outputs, right? So this can be used for image generation or text synthesis or audio creation. And there's also a category between supervised and unsupervised learning, which is known as semi-supervised learning. So here means that we have a small amount of labeled data with a large amount of unlabeled data during training, which is somewhere between supervised and unsupervised learning. And why is this important? Because in many real world cases, we have a limited budget for labeling data points or images. So let's say in the case of maybe if you want to train a classifier for medical image diagnosis, you may have a budget of, let's say, asking a physician to label 100 medical images, but you do have a total of 1,000 images. So in this case, one question is, which 100 images or X-ray images or MRIs we have to label here. And in this case, we can use the entire unlabeled data. So hopefully we can find some clusters and groups and find which images are more likely to contain some useful information. And once we identify them, we can now give them to a supervisor or a medical expert to label those medical images. So this is a very also interesting area where we can consider the fact that we have a labeling budget and it is usually impractical or too resource intensive to label all data points that we have in a machine learning problem. So in this course, we mainly focus on supervised learning problems, which you can think of these as making predictions. And supervised learning can be divided into two main types based on the nature of the label or output. If the label that we are trying to predict is a continuous variable, meaning a real number, this is what is known as regression. But if what we're trying to predict is a discrete variable, which corresponds to a category or class label, then this is classification. So here we have two different examples. On the left, let's say we have our input or our feature as the years of experience for some employees in a company. And on the y-axis is what we're trying to predict, which is the salary. So in this case, salary is a real number. And we want to know, for example, if you have a new employee with 21 years of experience, what the salary should be. So this is an example of a regression problem. But in classification problem, let's say we have two features, like feature one might be the number of times we have the word credit card in an email, and feature two is the number of times that we have, let's say, account number in an email. And based on these two, we now want to be able to say, well, if we have a new email with this number of feature one and this value of feature two, whether it belongs to category spam or not spam. So as you can see here, the goal is to predict a categorical output, which is a spam or not a spam. And although, this might be kind of like similar in terms of what we are doing in these both cases, there are key differences between regression and classification problems. And these differences are almost in all stages of learning, from the way that models process data, the way that they output predictions, and the way that we measure errors in terms of being able to train our model to make accurate predictions. And in particular, one challenge is that when we have these categorical outputs or targets, there is no obvious notion of distance between them, right? So in the regression, for example, if the output should be close to 2000 and I predict the value to be 3000, then obviously I can subtract these two numbers and find the difference. But in the case of classification, if let's say the true label or output of an email is a spam, and I predict it as not being a spam, then what is the distance or how much error did I make? We can't just simply say that this is one unit of error, right? Because these are categorical labels. Therefore, you can see that, definitely finding the error that we have when we have classification problems is definitely a more challenging problem. So just to recap here, we have two main types, supervised and unsupervised learning. And obviously we have a third case, which is between the two. And in this course, we mainly focus on supervised learning, where we have input features and output labels for all the training data points, which we can use for the training stage. And supervised learning also has two categories, regression and classification, depending on the nature of the output variable or the target. And then finally, in terms of another classification, we can divide machine learning models into model-based versus instance-based learning. And model-based learning means that we want to usually learn a model with a fixed set of parameters during the training stage. And once we learn those fixed parameters, now they remain fixed, and then we can use them to make predictions later on, to be able to make predictions for new or unseen samples. However, in the case of instance-based learning, it is more or less based on memorizing the training data. And when we want to make predictions and we have new instances or new data points, we're going to compare them to to these training data points that we have stored. And very, popular examples of this is k nearest neighbor. So because of this, let's start with the instance-based learning. So if we have this spam filtering system where we have two different categories or outputs, and we have a new email that we want to categorize, let's say if we choose the three nearest neighbors, then we can look at their labels. And since in this case, two of them are in the spam class, we can say that, well, this new email is in the spam class. And therefore, this is an example of instance-based learning where we perform such comparisons between new data points and training data points that we have stored. And the problem here is that during the training, we almost don't have to do anything because we have to wait until we get new or unseen data points, and then we do these comparisons. So therefore, the prediction stage is actually more expensive in instance-based learning. On the other hand, when we have model-based learning, and let's say we have these two classes, what we do is that first we assume that there exists a line that separates these two classes, and this line is parameterized or characterized by the slope and intercept. And once we find these two parameters, then for any new data point, it's just as easy as figuring out whether it's on the right side or left side. And based on that, we can make predictions. So this means that really during the training stage, we have to do the hard work to find the slope and intercept. That's an estimation problem. But once we get to the prediction stage, then we simply just have to see whether this new data point is or new email is on the right side of this line or the left side. And based on that, we can classify these new data points. So that's kind of like the main differences between model-based and instance-based learning. And through this course, we mainly focus on model-based learning approaches. And there are a few cases of instance-based learning that we will cover.